So we're talking about how to work with vectors, and so far we've basically just seen how to work with them in 2 dimensions. What we're going to start talking about today is, well, now if we up the number of dimensions, how does that change things? Pretty much all it does is just add a z component, a third component to everything we've already been doing. It does change a little bit of the looks of things, and it's definitely harder to graph this stuff and visualize it, but it doesn't really change a lot of what we've done so far. It just adds an additional step onto it there. So here in the first beginning of this is just some parallels between the 2-dimension and the 3-dimension, either what we call it or what it looks like there. So in 2 dimensions, we have a plane, which makes sense. We've got an x component, a y component, and a plane. In 3 dimensions, we have a space. We've got an xy plane, the normal one. Then we also have a yz plane, where those 2 axes intersect, and a xz plane. I will show pictures of these in a little bit here, so I'm working with right now. Instead of just having an ordered pair, which we are familiar with, now we have an ordered triple, because it has 3 terms instead of 2 terms. Z, as you can see, is the next letter that we use to represent this 3rd dimension that we're adding here. In 2 dimensions, we have 4 quadrants. In 3 dimensions, we have 8 octants, because it's split into 8 regions there. Distance, we know how to find in 2 dimensions. In 3 dimensions, you know, distance is almost the same exact thing. So all of this part here is exactly the same as it was in 2 dimensions. We just add that z component to it. So we're really doing the same thing. I'm not going to try to go through and prove these things right now. We'll just kind of take some of the stuff as is. Circles don't change a whole lot too. Again, you'll notice a lot of parallels. A circle in 2 dimensions has the x component. What does x0, y0 represent over here?
The origin.
Or not just the origin, but the center of the circle, okay? Which if it is the origin, it's just a bunch of zeros, so it makes it easy. But yeah, the center of the circle, right idea there. And so similar idea if we move over to 3 dimensions, again, you see we have that same stuff showing up over here, but now we've got that 3rd component, and so we just do the same thing for z. We just tack it on. We are working with a sphere now, so just a circle. We'll talk more about kind of the graphs and things as we go. We notice midpoint, the same thing happens there. So a lot of parallels between what we do in 2 dimensions and what we do in 3 dimensions. Now I mentioned it doesn't really matter which way we go through and graph these, but just for consistency, our book uses the right-hand method, which I put a little graph of right over here. Essentially, we're going to have the positive x-axis pointing towards us, the positive y-axis going off towards the right, and then we'll always draw the z-axis going up when we sketch these things here. Occasionally, so like in a left-handed system, these things would be flipped around the x and the y. The reason it's called a right-handed system, support. If you imagine just kind of working your way up in dimensions, okay, and on your hand, your thumb is basically like your first dimension. You've got one positive direction you can go. If you think about your pointer finger then as your 2nd dimension, your y, you have your x-axis and have your y-axis. And then your 3rd dimension would be your z, and that's what this represents over here. And so if you kind of do that with your hands, with your if you do that with your hands on your right hand, you get the same picture like we have in the notes here. But if you do it on your left hand, let your thumb be your x-axis, then your y-axis and your z-axis, just your x and y are backwards. So that's why it's called right-hand system. I don't know if this is helpful when you're trying to think about graphing something. That's at least where the name comes from. So we'll be consistent. We'll always have the x-axis pointing towards us, the y-axis going off to the right, and the z-axis going straight up there. Okay. The link I have in here didn't work just now when I tried to go through and do this, but I've got a better link anyway. Plotting points in 3D is tricky on a sheet of paper because it's not, you lose the depth, obviously. So when we're plot these things here, sometimes we'll sketch them on paper, sometimes we'll just use technology to go through and graph these things for us. But I am going to go through and graph these things on technology, not on paper here. That GeoGebra app that I showed the other day will do a better job of graphing this than the one I had in there anyway. So geogebra.org/3D. Let me write that in the notes too. Oh, and there's the rest of the quizzes. So much easier. Okay. So instead of the link that's in your notes, we're going to use this link instead. I don't know if I spelled it right. I'll go check in a minute. If you've used Desmos a lot, Desmos is wonderful, and I love it, but this is like the 3D version of that. It allows us to do a lot of the same type of stuff here. But I think I may have skipped a letter. Let me check the link. Yes, there should be an E between the G and the B. Sorry. So I skipped that one. So anyway, we'll use that. We'll go ahead and plot this. But just to kind of get a visual of like what we're doing when we graph these. But again, if you know how to graph 2D points, you're going to start off the same way. Your first 2 numbers in these ordered triples are just your x and your y. And then your 3rd one tells you your z, which goes up and down there. Okay, so let's go ahead and plot these guys. So first point is 1, 4, 7. And we just use parentheses like normal. So 1, 4, and you see that little blue dot popped up now once I've got that 7. I need to zoom out a little. There we go. Okay, so along, let's rotate these to match up with what we have. So this red line here is our positive x-axis with a little arrow on the positive end. The green has a positive arrow on the positive y end, and then the blue is the z up and down there. There are ways you can get this to label the axes here, but I won't do that right now. So it is oriented the same way we want, and you can see there's that little blue dot. Right now, if we were to look at this, let's see if we can get to it. Okay, if we look at it kind of this way, that red line is the x-axis, that green line is the y-axis. This is just traditional two-dimensional plot. If you go through and plot the point 1, 4, you get this dot right here, and that's what we're working with. Really what we're doing is say, okay, well, it's not just this top-down view, but now we've got that height on it, and that's what that z represents. It's just pulling this thing up a level. But if you just imagine looking straight down that z-axis, you're just looking at your regular x, y plane.
So why would we look at, I mean, just wide setup? Why? Because we've always looked at x, y as y and x.
Mm-hmm.
Why would we flip that down and then go up? Instead of doing it out?
That's a good question. That's just kind of always how it's been done.
I didn't know, but because it's kind of weird now looking.
I guess the idea is thinking like this. If your XY plane is still looks like a sheet of paper, then we're still drawing the XY on that sheet of paper, but now what we're doing is we're adding this up dimension to it, and that's what the Z is representing. So maybe if you think about that, it kind of makes sense. It's just kind of traditionally how it's done. But I see what you're saying. It would make more sense to have your XY this way, and your Z kind of be the one that changes.
That's what, like, with spheres and stuff, that's how you always picture it come out of it.
Yeah. So let's imagine that we have our sheet of paper is what we're laying things down on. So instead of like the XY plane being here, we've got to lay it down. But yeah, it is a little different. Yeah. I don't know why they decided that's the way to do it, but that's just kind of how this is. Oh heavens, let's put this back where it goes. There we go. All right, so there's the first point. Add a couple more points here. If we add the point -5, 6, 0, what's that -5 mean we're going to do? So the second point in your notes, how am I going to plot that?
So you come -5.
Yeah, we're going to go backwards on the x-axis. So we're going to travel from -2, -4, we're going to be -5. And then, 6 on the y, so we're coming out. And if our z component is 0, we're not lifting off the xy plane. We're just sitting on it right there. Okay, so all the same conventions you would have for graphing things. You can see that point B is right there on that plane. It's just we have a third one to worry about here. And the last one, -2, 0, 10. Type it 2, 0, 10. Okay, so similar thing with this one. Let me zoom out a little more so we can actually see the points. Okay, we went -2 in the x direction, right? So backwards 2. We didn't go anywhere left and right for y, so we just went straight up. So if we were to rotate this guy, you can see right here that point C didn't move anywhere in the y direction. It's right there on that plane. So I don't know if it helps seeing the points like this, especially when I move it around too fast or everything gets all jabbled. But we'll try to look at these things three-dimensionally. Just like your calculator won't plot, so if you have a fancy calculators won't plot points in 2 dimensions. They don't really do, well, they can, but not easily. Same thing with 3-dimensional points there. They're mostly going to be useful to graph like surfaces and stuff like that, which this will do both. So hopefully that doesn't make things look more complicated. Okay, but plotting points. We're not going to plot points as much as we're going to plot surfaces. We just kind of get used to seeing it. Distance between 2 points, like we said, is really the same way you find distance in the 2-dimensional space. You just tack on the same idea for the z component there. And again, I'm not going to try to go through and prove why we do it that way. That's just kind of the way we do it. But you can imagine if you've got 2 points, you're still just creating a triangle in between, and your triangle's just not on that xy plane anymore. It might be somewhere else. So that's why it's a very similar idea to what we had before. So to find the distance, we're going to have 1 minus -5 quantity squared. Let's put 2 plus 4 minus 6 the quantity squared plus 7 minus 0 the quantity squared. So what does that give us? 1 plus 5, so we have 6 squared or 36. 6, 4, it's 2, so that gives us 4 plus 49. The square root of 89. Which I don't think can reduce. I think 89 might be fine. So we're done with that one. Okay. So if you think about just this, you're pausing for a minute. These points could be the start and stop point for a vector, right? So we can say maybe the vector starts at 1, 4, 7, and ends at -5, 6, 0, which means this would be the magnitude of the vector. So we're going to see a lot of the same type of things in 2 dimensions that we saw in 3 dimensions here. Okay, we're still going to look at vectors, still going to look at lengths, all that stuff still stays the same. Right, find the equation for a sphere with these points as the endpoints of diameter. So just like in algebra classes, you try to throw out different pieces of information and keep it together to make the equation for a circle, we can do the same thing here. If we throw out pieces of information, we just kind of piece it together and think about what this is going to mean for the equation of a sphere here. So if I write the equation of a sphere, just a general form from the previous page over here, and if you don't want to copy this over, that's fine. And everything is still squared, even though we're 3 dimensions, we still stick with squaring everything. Again, what does x0, y0, z0 represent?
The center.
Mm-hmm. Are we told the center?
No.
No. How are we going to find the center?
Midpoint.
Yeah, midpoint between these 2 points here. Now, I obviously haven't seen much work from you guys to know if this is a problem there, but a common problem I see with students when they find midpoint is trying to do slope type things. Midpoint's just the average. You just find the midway point between 2 things here. So all we're going to do is add the x parts together and find essentially the average of the x's, find the average of the y's, and the average of the z values. So make sure you are adding 5 plus 0 and then dividing that by 2. So for the x component, we'll have 5 plus 0 divided by 2. For the y component, -2 plus 4 divided by 2. And for the z component, 3 plus -3 divided by 2. So we're just finding a bunch of averages. So we get 5 halves, 1, and 0. So there we go. Now we have a center. We can plug those 3 numbers into our equation, and we are almost done. What are we missing? So I should be more clear. We've got this x0, y0, z0. That's going to be these numbers right here we just computed. So to write the equation of a sphere, there's one thing we're missing still. Radius. How are we going to find the radius?
The distance between them.
We've got some options. We also said we can do a distance between the midpoint and a point. What else could we do? Here's some people talking to Siri. Talk a little louder. A little louder.
You got to square root of both sides.
Say that again?
Find the square root of both sides.
Yes, find for both sides, and then we can go through and divide by that. Okay. So, oh no, you said square root of both sides. I see what you said. No, we don't want to find the square root of both sides. Right now, we're just saying what is the radius. So that's the question we're trying to figure out: is what is that number for the radius here? Russell said we can find the distance from our midpoint that we just found to one of the endpoints. And I was just trying to ask, another way we can do it is you can just find the original 2 points and have that. You can take the diameter and have it. I don't know what's here. Both are fine. So distance, let's go midpoint to endpoint there. We don't really need to worry about square rooting this. We'll just leave it as is. Just because this has zeros in it, I'm going to go ahead and work with this number. The other one we just find, it's just more zeros, a little less stuff to write down here. So distance from our midpoint we just found is 0, 4, -3. We'll get what? The square root of 5 halves minus 0, so 5 halves squared. 1 minus 4, so -3 squared, and 0 minus -3, so 3 squared. So what does that give us? We've got 25 over 4 plus 9 plus 9. 9, I'm just going to use a calculator for this. Okay. So just for that square root, we're going to have 25 divided by 4 plus 18. So that's a square root of 97. Yeah. The nice one from your calculators, they leave it all in exact form and simplify it for you. Let's do it. Sure. The square root of 97. The 2 is not in the square root. They've simplified that down. So plugging all this stuff in to find the equation of the sphere, which is actually what the problem asked us to do, we're going to get x minus 5 halves, since that's our center, squared, plus y minus 1 quantity squared, plus z minus 0, so just z squared, equals, and then what we have now is just our radius, so we really didn't need the square root part, but just think about going back and squaring both those, we'll get 97 over 4. So equation for the sphere. Now I mentioned the first day of class that we'll talk about different coordinate systems. And the same thing we saw between working with like rectangular coordinates and circles, going to polar coordinates and circles, it's got so much easier to write those equations. We're going to see really similar things when we work with 3 dimensions too. We're going to be able to say, okay, this is a rectangular coordinates equation for a sphere. It works, but it's kind of clunky. Okay, there's a lot of stuff going on here, there's a lot of parts to kind of keep track of there. When we move to our polar coordinate version of this, which is actually called cylindrical coordinates, it does help a lot. But there's an even better way we can work with this when we work with spherical coordinates, which really simplifies this thing down a whole bunch here. And so we will work with spheres, but we'll kind of see them in different contexts. So not always going to be worked with as rectangular equations. We'll have different ways to go through and work with those. But hopefully this looks very similar to problems we would have done in algebra type class. Just want to show that we can do very similar things with 3 dimensions. It doesn't change a whole lot. Questions so far?
Yeah, so if I find it a pinpoint, do you just choose any one of the points, like the coordinates given?
So like for this part right down here?
Yeah.
Yeah, either endpoint's going to work because really what we're doing is trying to find the radius. We want to go from the center, which we just found is this guy right here. We want to go from that center anywhere to the outside. And we were told that both those points we were given at the beginning were outside points there, so just pick either one of them and use those. The only reason I picked 0, 4, negative 3 is just because it's 0 in it, so the algebra will be a little simpler. If you use the point 5, negative 2, 3, you should get the same exact value for it. It shouldn't change it at all.
Okay.
So either one of those endpoints would work.
All right. Thank you.
No problem. Anything else? All right. So let's get to vectors. I hinted a little bit about how this is very similar to vectors. So let's actually start seeing those there. Really all we're going to do is say, okay, everything we did, just tack on that third component. So we're still going to talk about working with this in component form. And we're just going to have not just V1 and V2, but then V3. We have to have some Z components on there. But we know that component form, if I can talk correctly, component form still starts at the origin, which now is just an ordered triple. Okay, so basically we're told the endpoint, we have the origin, same thing there. If we want to find the magnitude of this vector, same exact notation comes in. You use a little double bars around V, which is why we kind of have different notation there. Doesn't matter what dimensions you're working with, and you find it the same way we just found the distance before. So not a whole lot of changes there. I left a lot more space I need to for this 0 vector, which we can call 0 with a little bar over it. But this is just in component form a bunch of zeros. Okay. Doesn't show up a whole lot, but it is still technically a vector. Adding, subtracting, all the stuff we did with vectors before still applies here. When we're adding vectors, we're still basically saying, okay, do this one set of directions, and then from there, do the other set of directions. Whether we're in 2 dimensions or 3 dimensions, it's still just telling us how to get around there. It's just now instead of going left and right, we have options to go up and down with it too there. So a lot of these things are going to be pretty similar. Okay, I didn't even put in the formulas for all those things there. Some additional things that hold true. So let's say we have 2 vectors, u and v. U does not necessarily have to be a unit vector. Okay, the book uses u for unit vectors and other vectors too. But then some scalar. Again, scalar just means some number here. So if 2 vectors are equal, okay, then we're going to have, I'll list it there. 2 vectors are equal if only if those numbers are all the same. Okay, so when we're in component form, these vectors are equal, obviously only if the numbers are the same. If you've got one vector that's say 1, 2, 7, another vector that's 1, 2, 10, they're going to different places. They can't be equal to each other. Now, we talked about vectors being equivalent by being able to look at magnitude and slope, and that's all still true. Same thing happens with this. But since these vectors are already given to us in component form, we're not really checking that. Okay, it's just simply checking to make sure the input is the same. So hopefully number 1 is pretty obvious. Component form is saying the same thing. This is still saying that we're going to take terminal point minus initial point. So no difference at that point we did before. Just mention components. Take the x minus the x, the y minus the y, the z minus the z. It's all the same things there. Length, same thing we saw before, nothing really different for finding magnitude. Unit vector, same thing we saw before. We're going to find the magnitude of our vector and then scale our original vector by that amount there. We know that multiplying dividing by a scalar is just going to change the length of it. Addition doesn't change, the multiplication doesn't change. All that stuff is still basically the same. We're doing the same thing, just have a third dimension. We're not going to work with examples more than that, but if we were to add a fourth dimension or a fifth or a sixth, all these properties still work. Okay? And that's what makes vectors so nice, is you don't need to develop a new set of rules when things get more complicated. Thinking about a four-dimensional surface or something like that is a little weird, but in application, it makes total sense. If your V1, V2, and V3, your X, Y, and Z are representing different variables that can be impacting something, it's not absurd at all to imagine that the price of a house is impacted by, say, the number of bedrooms it has, the age of the house, as well as like the number of bathrooms or the lot size or things like that. There's a ton of different things that can impact this. So when we talk about like 4 dimensions and 5 dimensions, it's less in that geometric sense and more in that there's a lot of stuff that can be impacted in this. But again, all of this stuff still applies to higher dimensions. We just don't do a lot of the examples with it because it gets kind of long and hard to do. All right, so there is some practice to this. If I said it was basically the same thing, why don't you guys try this and see if you can get the numbers out okay? So example 4, example 5, let's see. Yeah, and then we'll talk about parallel vectors. So just go ahead and try these two on your own, and then in a minute or two, we'll go ahead and see how we do on that. And I think I may have all the quizzes back too. So we can go ahead. But go ahead and try those out. Let's go ahead and come together. We can mostly discuss number 5. Didn't write it all down. You can write as we discussed there. So component form. What did you get? We'll just look at the answer and see if there's questions. So what did someone get for the component form example 4?
2, 4, -7.
Does everyone agree with that? Get the same thing?
Yeah.
Okay, so like I said, terminal minus initial, just use the component form here. To find the unit vector, we're going to need the magnitude. So we'll just put that step in there. So what was the magnitude of this vector? Okay. square root of 69, which means then to find that unit vector, which if you want to call u, that's cool. I'm just going to go ahead and actually write out unit vector. I don't want to get in the habit of u always being unit vector here. We're going to divide each one of those components by square root of 69. So one way you can write it would be 2 over root 69, 4 over square root of 69, and negative 7. If you want to write it in more factored form, that's fine too. That's square root of 69 out, 1 over square root of 69 out front, that's okay also. Okay. Like I said, we don't have to verify it's a unit vector. We can trust that we did the math right. But if you were to go through and find the magnitude of this, you'd see that you get a unit vector for sure. So, basically the same as before, just one more little piece you're doing on there, hopefully. So example 5, consider the following vectors. We've got u is negative v, w is 2 times v. We want to know how these relate back to the original vector. So we're not really given any component form for these different vectors here. So let's start off with u and v. What's the relationship between those two guys? Or this first expression, what's happening here?
They cross each other. Perpendicular.
Not quite. They don't cross each other. If you think about vector u and v. So v is
They
the
go
original
opposite
vector.
direction.
Yeah, they go opposite directions. So you've got some vector v doing something. And basically what this is saying is u is being defined as a negative v. And so really all that's doing is still, points are still going to be the same. We're just going to go in the opposite directions there. So v goes from one place to the other, and then u just undoes that. It just works backwards from there. So that's all that's really doing here. So this means u is going in the opposite direction of v. They have the same start point, or same points to start and end at. They just reverse which one's starting and which one's stopping. Okay. All right, how about w? How does w relate to its original vector v?
2 times right.
Just been stretched out. So same starting point, it just does vector v and then basically does it again. It's just going to be twice as long as vector v. So what this kind of leads us to, and the next thing kind of defines it, if we think about things being parallel, okay, we all know what it means to be parallel there. Are these vectors parallel? Say like w and v, are they parallel?
You don't know.
Kind of have to like modify. So like, what is parallel mean? Let's just, I know we all know, but just say it. Parallel means what?
2 lines.
Never me. So in terms of like working with linear equations, they have the same slope. Okay. How does slope relate to our vectors? We said slope and direction, like the same type of thing, right? So if we have two vectors that are going in the same direction, remember, component form is just a way to say, well, I've moved them to start at the orange there. Orange, my goodness. Origin. We can shift these vectors around and they're still going to be the same vectors there. So let's say I have this vector w and this vector v, and right now they're kind of on top of each other. But if I were to just slide them apart a little bit, are they going to be parallel?
Yes.
Sure. Okay. How about vectors u and w, or u and v, the first two we looked at? Right now, again, they're just on top of each other because one's going one way, the other's going backwards. But if I shift them apart a little bit, they're still equivalent vectors, but are they parallel?
Yes.
Yeah. So when we talk about vectors being parallel, really all we're doing is we have one vector, and then we just multiply by some constant. If that vector has been multiplied by a constant, we know that the value is just going to make it longer, shorter. We just saw negatives, you're going to flip it around and make it go in the same direction there. But it's still going to be a parallel vector if we slide these things apart here. Since we're working with component form, yes, they do overlap basically every single time, but we know we can spread them apart, we can shift them a little bit, and they're still going to be parallel vectors here.
Now for w and v,
Uh-huh.
do we know that that they can be parallel?
Mm-hmm.
Because we don't know the slope of w.
That's true, but all we've done to find w is take vector v and make it twice as long. It's still going in the same direction, it's just going for longer.
Okay. We can assume that's going in the same direction.
Yep, it has to be going in the same direction, because all we did is we said, okay, well, right now it has a length of 1, we're just going to drag this thing out and make it have a longer length there. Like, think about it in a two-dimensional case here. So let's say if vector v was 1, 2. Let me get something. Let's 2's are nasty, because 2 times 2 and plus 2 is the same. So let's say vector is 1, 3, right? What's the slope of this vector? I know slope is a weird thing to talk about, but slope of this would be 3 minus 0, so 3 over 1, so it'd be just 3, right? If we go through and do this definition for what w is, w now is going to be 2 times this vector, so it's going to be 2, 6. And again, if we find the slope of that, what are we going to get? We're going to get the same thing. Okay, so yeah, when we go through and stretch this insurance, it's really just making our fraction for slope bigger or smaller, but it's still going to be parallel. So yes, we can still do it. The nice thing about this is it's really easy to see if we have parallel vectors and to prove we don't have parallel vectors. We don't have to go through and find slopes every single time. We can just say, okay, well, component form is often what we're working with. Is one a multiple of the other? So for example, 6 here, we got vector v starts at 0, 0, 0, this is component form. It goes backwards 6 on the x-axis, forward 8 on the y-axis, then up 2, and we have this vector. And what we want to know is, are either of these other vectors parallel to it? So pretty much what that's asking is, there a number I can multiply v by to get vector u? If there is, it's parallel. If there's not, it isn't. Is there a number I can multiply vector v by to get w? If there is, it's parallel. If there's not, it isn't. So there's no real magic to doing this. Just look component by component at these two guys here. So we're going to start off with v. We want to know, is there something times vector v that equals vector u? That's the question we're trying to answer here. So if we start with negative 6 times what gives us 3?
1/2.
Yeah, negative 1/2. So let's try negative 1/2 and see if that works for everything. Okay, so negative 1/2 times negative 6 does give us a positive 3. We want that. Negative 1/2 times 8 gives us negative 4, which is what we want there. And negative 1/2 times 2 gives us negative 1, which is vector u. So yeah, these two guys are parallel. Okay, they're going in the same direction. We simply are saying that u is shorter than v, and that u is just going in the opposite direction, but they're still parallel. They would lie on top of each other if you started them at the appropriate spots. So this is basically saying that means yes, u and v are parallel. And again, there's no real test we're doing for this, and that's not a complicated procedure. It's just, does it work or does it not? So do the same thing for w, just on your own, see if you can think through this and check real quick. Is there something I can multiply v by to get vector w?
No.
It almost works with a negative 2, but the last term has the wrong sign. So this one does not work out. Not. So no value c exists. Makes this true, so u or v and w are not parallel. Before we do this third one here, let me see if I can quickly graph these guys so you can visually make sure I understand here too. Vectors. I don't know. I don't do vectors in here very often, so just give me a minute to make sure I do a vector right. Oh, it's just that. Okay, that shouldn't be too bad. So vector starting from point 0, 0, 0. Let's put my parentheses as I go. All right, vector v for this problem is negative 6, 8, 2. So let's see if this works. Okay, good. Let's take these guys off. All right, so there is that vector v that we were just working with there in that previous problem. Oh, don't just stand still. Okay, and so we went through and we found that u was parallel to it. So if I graph vector u, u also started at 0, 0, 0. I think I just put the endpoint, that'd be okay too.
3.
Okay, it may be kind of hard to see from here, but I'll try to spin it and see. So this is the other vector u, and you can see that these guys are just basically in a line, right? I mean, one of them is going the other direction than the other one, but those guys are just making a line with each other. And so that means they're parallel in vector land. They're going in the same direction. Direction is really all we're caring about when we're talking about parallel vectors. And if you were to imagine them on a line, then yeah, I shouldn't say direction, because they're not directions. They're on the same line. Their line has that same rate of change there. So that's why we can show those, say those two guys are parallel to each other. If I go there and throw in that last one, w, that we said was not parallel, what were the points for that one? Or the endpoint for that one?
12, negative 16, 4.
Okay, we can see that one does not fit in here. Okay, that's breaking off the path. It's not going in that same line as the other one, so it's not parallel anymore. If we had that negative sign, right? 'Cause that's all that was off is a negative sign here. Is that what the problem was with it? Yeah. Okay, if we fix that negative sign, now it does work out okay. So if the information we were given for W is that was 12, negative 16, negative 4, then it would have been parallel as well. Okay, so does that kind of make it a little easier to see what's going on there with parallel vectors, hopefully? Okay, we're talking about them basically, are they on a line with each other? And we can see that, yeah, those first two are aligned, but that definitely one jumps off different direction, obviously not that. Okay. So, quick check is looking for that scalar. If we have a scalar, we can multiply 5 and know it's parallel. If we don't, then it's not parallel. It's as simple as that. Instead of talking about that collinear thing, we'll wait and talk about that tomorrow to kind of tie in from this. I want to real quick go over the quiz, and then if we have time, I forgot I was going to go back and mention that little piece we ended with last time. But let's talk about the quiz, because I have everyone's information. Okay. And some of this hopefully is very easy now that we've been talking about it since we were just doing this stuff here. Component form, we'll just look at the answer for this one, and hopefully everyone remembers if it looks familiar or not. So endpoint minus initial point, you should end up with negative 6, 4 for that. And how do we find the magnitude? Yeah, distance from it. So we're basically just going to square both of these. We're going to have the 6 squared plus the 4 squared, and that eventually will simplify down to 2 squared and 13 is what it reduces to. Yeah, 54 in between there. So just explaining, what does this mean? The length or the magnitude, either one of those would be fine. Distance, if you said distance between the origin and the point, that would be okay too. And then I won't go through and do all of it, but to find the unit vector, what would we do with the information we have? Yepers, and since we've got 6 and 4 are both even, we can reduce it down to write in the lowest terms there. But yeah, it's just a 6, 4 divided by 2 root 13. Okay. All right, so then the other piece that we skipped yesterday, we talked a little about this, but I said we'd come back and revisit it here. So the example we did at the end of the hour, we had this ocean liner that was being pushed by these 2 tugboats. And the tugboats were applying the same amount of force. They were making the opposite angles of each other with this ocean liner, and so the ocean liner was just moving straight over there. And just real quick here, since I've got the calculator pulled up, I'll type in one of these equations so you can kind of see where the numbers came from. But when we went through and say, like, if we're finding the 400 times cosine of negative 20. I think this is right now in radian mode still. It's somewhere, I can tell to do degrees. I don't remember where. I can't convert them that quick. Change this. Okay. All right, so cosine negative 20. Approximate. Do that too. All right, so if we just had that first component for F1, we would have had 375.88 about. If we do 400 times sine of negative 20, that gives us negative 136.8 about. Okay, and so that would be the force from the first tugboat. That's its vector. That's what it's doing there. If we simply go through and find it for the second vector, we're going to see that the 4 times cosine of positive 20 is also 375.8. When we add those two together, that's where that 751 comes from. Okay, 375 plus 375 gives us that with the decimals on there. But when we go back and do the one for sine, that's where we saw this. So sine of positive 20 was, oops, it was a positive 136. And so like we said, those two components canceled out there. If we were to change this just a little bit, so let's say one of the tugboats wasn't coming in at the exact same angle, they were just off a little bit from that. So let's just move to, like, say 19 degrees instead. Now I know you guys know you're not going to get the same number, but we'll do it anyway. Okay, so now we're off by 6 there. So if we think about how that changes things, and I have to change the cosine part too. But now what's happening is one boat's pushing at a slightly different angle. Tugboat's almost going straight, but it's going off at a little bit of an angle. Okay, so little differences make a huge difference in how we go through this. But that's kind of where those numbers came from. I just want to make sure it was all clear. I know you guys mentioned it, but I want to go back to it. Okay. So we do have class tomorrow. I know for you guys, you don't have other classes, but we do have class tomorrow. We'll finish up section 11.2. I don't think we'll start 11.3 yet. What I'll probably do is send out a practice worksheet. We'll just do some things in class to make sure everyone's comfortable with the basic operations before we move on with that. Okay. So if you have any questions, let me know. Make sure you're working on the homework. If you can't get in there or some problem happens, just keep me aware and I'll try to help out.
Homework just 11.1, right?
No, homework is 11.1 and 11.2.
And 11.2, yeah, I should be able to do all.
Yep, you should be able to take care of all. So I just, whatever we covered about that week, I'll put in one homework assignment for the week. So it's not section by section, it's just like week by week. It's just less stuff to think about.